Assalamualaikum and good day everyone. Okay, we will cover the next whatever left that should be covered in week 4. Okay, previously we have covered about potential difference, absolute potential, and the introduction to the idea of energy exchange. So next we will go into the coverage on the method of calculating energy storage in a field, and also about potential gradients. Okay, so this is the last things that should be covered in week 4. Okay, so we go to the related page. Okay, so you can open page 149. Okay, page 149 if you want to read further. Okay, in fact you need to read more, okay, because this is Sadiku will explain in detail. Okay, so now you want to see about we want to see about the relation between E and Maxwell equation. Okay, so we notice that when we are trying to find the potential difference, okay, for example, if you have your A here, the point that you want to measure, and the point B, okay, and let's say you have your charge here, okay, so you want to measure the potential difference. You notice that the value that you take from here is the same if you take the value from here. Okay, so it is independent of path. Okay, so your VBA is equals to negative VAB. Okay, so they are independent of path. So if we notice that if we take this one and this one, they form like a closed path. Okay, they form like a closed path. So if we take the integral of the closed path, okay, we will obtain 0. Okay, what does it mean? This means that no net work done in moving a charge in the closed path. Okay, remember, from the beginning until up to now, we only discussed about electrostatic. Okay, so these equations that we study is related with electrostatic. So if we go further into the electromagnetic, maybe it will change. Okay, we will have some changes. Okay, so you have your V equals to negative VAB regardless of path. The potential difference are the same. Okay, it's independent, and if we take the integral of the closed loop, it results in 0. Okay, and then we're applying the Stocks Theorem. Okay, the Stocks Theorem we have here, we will have, like for example, in this surface, okay, then we have the del curl of E, okay, ds will also result in 0. Okay, now after that we are introduced about the concept of potential gradient. Okay, the concept of potential gradient. Okay, so here is the electric field intensity, and this is, you know, right, is your del operator, and this is your V. Del dot V, we call it gradient. Okay, so that's why this we call it potential gradient. Okay, okay, now you can try to see from the exercise. Okay, from the example. Okay, this sample is straightforward for your understanding. Given the potential V equals to 10 over r squared sin theta cos phi, find the electric flux density at D, and find electric flux D density at 2 pi over 2, 0. Okay, first when you get this equation, you have your V, right? Okay, then what you can do is that you do the del. Okay, negative del V, or the potential gradient, then you get the value of this. Okay, the vector. Okay, so this is your vector. Okay, and after that, you know that D is equal to epsilon naught E. Okay, so you can just directly insert this into your equation here. Then you have your D. Okay. Now, then this question is that calculate the work done in moving a 10 microcoulomb charge from point A to point B. Okay. So what we have learned on the work done is that we have the equation that we can use. Okay, E dot dA, right? So this equation is the work done is we want to move a 1 point charge, so it's W over Q. Okay. Then you can see from the examples. Okay, if you guys don't understand, please feel free to let me know. Okay, so that is what it's all about potential gradient. Is pretty quite straightforward. Okay. So, okay, before I forget, this is the when it mentioned about conservative nature here, when it's mentioned about conservative nature, you see this is a closed path. Okay. It is considered conservative because the vector does not depends on the path of integration. You can see, right? If you take from here or you take it from here, and it is conservative. Okay. So the next part of the lecture, okay, the one that is more detailed compared to the potential gradients, okay, is the energy density in electrostatic field. Okay, so energy density in electrostatic field. Okay, remember up till now we only learned about electrostatic. So imagine that you have a point, you have an area here, okay, from infinity, okay, so first let's say you want to carry a 1 point charge, okay, from the infinity towards a point 1 here. Okay, so means initially it is neutral. Okay, we don't have nothing, we have nothing. What does it mean by neutral? Means there are no electric charge. Okay, there's no electric charge. So what, the space is initially charge free. Now we want to carry Q1 to this direction. Okay, to here. So the first work done towards to this area. Okay, for example, for this case, we W1 is equals to 0. Okay, because the charge, there is no work required to transfer Q1 from the infinity to point P. Okay, because the space is totally charge free at that time, at that point at time. Now the next is that we want to carry, okay, we want to carry another point charge. Let's say we have a point charge 2. Okay, now at position 2. Now the charge Q2 start experiencing what? It start experiencing the potential. Okay, the potential due to the Q1 direction. Okay, Q1 charge, because Q1 is already there. So for this kind of situation when we have Q2, so we have WE equals to W1 plus W2. Okay, so what happened is that this one is initially 0, right? But what happened to W2? W2 is Q of the charge Q2, and then the potential due to Q1. Okay. Similarly, if you have another Q3, okay, we want to bring Q3 to P3, it will experience potential due to P1 and P2. So WE equals to W1 plus W2 plus W3. Okay. Okay, here is 0. Then what is your Q2? Q2 and potential from point 1 to point 2. Okay, and then the next one you have potential, the combined potential for V31 plus V32. Okay, potential from point 3, from 1 to point 3, and potential from point 2 to point 3. Okay, addition, and it acts on the Q3. And then we elaborate the equations, okay? If the charge were positioned in reverse order now, if we have in reverse order, okay, similar question, but if we put W3, W2, and W1, if we reverse it, okay, then we experience like W3 is 0, Q2 you have here, and 3, potential 3 to point 2, from point 3 to point 2, and this one, okay. So expanding this, okay, then you will learn this actually for the point charge, okay, like what I taught you guys. For the point, it is using sigma, but it's continuous, we're using integral. So to summarize, we will have half of k equals to 1 and qk vk, okay. This will be your the total work done, okay, for the point charge. So it will be measured in joule, okay, just like you guys know already, okay. This is k. If the charge is 1, you have 1 here, okay. Vk 1, q1, v1, okay. So this is the first equation to obtain your W. And then you also have equation W half of d vector E and dV, and you have another equation which is this one of V epsilon naught of E square dV, okay. So this is, we can tell this is the energy in the system, and it is also the energy stored in the system, okay. It means the same thing, okay. So we try, for example, for practice exercise 4.16, okay. We try, okay, now we try the 4.16, okay. Point charges Q1 equal to 1 nanocoulomb, Q2 92 nanocoulomb, Q3 3 nanocoulomb, and 4 94 nanocoulomb are positioned at one at a time, okay, one at a time in the order of this position, okay. Calculate the energy distance after each position, okay. So what happened is that okay, first he put Q1, okay, first he put Q1 at the origin. Okay, we try to imagine the situation, although we may be able to solve directly, but we try to imagine the situation, okay. So at origin, okay, and after that, it put the second charge, which is -2, okay, at this position, okay, means this is what happened at the first time, okay. So at the second time, the Q1 is already there, okay, and now it's introduced Q2 at the position of 100, means 100. This is your x, this is your y, this is your z. So it is put here, okay. This is your Q2, okay. At the third situation, remember the two charge that initial there is still there. This is Q1 and Q2. Now it put a second, it introduced a third charge at this position, 0 0 -1, 0 0 -1. So here, okay, -1 because it is here. So this is your Q3, okay. And after that, the point Q4 is introduced then. Okay, then and another one is Q4 is introduced at 0 0 1, 0 0 1. Okay, so this is the situation, okay. So we will see in timely event, okay. First it is totally empty, then we introduce Q1, okay. So what happened is, when after Q1 is placed, okay, there is no potential experienced by Q1. Why? Because the charge here is initially free of charge, okay. So that's why when after Q1, your work 1 is 0, because there are no potential exist. Then when we start introduce Q2 inside here, there is already potential due to Q1. So we have after Q2, we will have what is work done, okay, in taking the position Q2 to this position, okay, is experiencing the potential. So it's actually W2 equals to Q2 and potential to Q2 from point 1, okay, from charge 1. So then you have your Q2 here, okay. Then what we learned from the previous lecture, okay, we have Q is actually equals to V equals to 4 pi epsilon naught R, right? So R here is the magnitude, okay, the magnitude. So V to 1. So what is actually is Q1, okay. So this is Q, okay. And then after that you have 4 pi epsilon naught. So how we obtain the R? It's just simply the distance, okay. So here you have first is 0, 0, 0, okay, due to the position. And then what? And then the second position is 1, 0, 0, okay. So solve this, you get, for example, if you get your x, okay, if you get the answer in x. And after that, when we introduce the Q3, okay, when Q3 is now inserted, now you begin to have work, okay, which is initially just now you have Q2 V to 1. Then the next one you have what? You have charge experienced by Q3 from the potential due to 1 to 3 plus potential due to 2 to 1, okay. Sorry, 2 to 3, okay. Then similarly, okay, you have this one, right? You know this one, you directly x plus this one, you just further elaborate, okay. So you have your Q3, then you have your, what is here? It is your Q1, right, over 4 pi epsilon naught, your magnitude. And you have your Q2, 4 pi epsilon naught R, okay. This one is R due to 1, this R distance due to 3, and this one is due to 2, okay. So, and after that, when you have Q4, what happened Q4? Q4, we add it another, okay. So it's just like a summation. If you have your Y here, then after Q4 is just like another combination. You further expand. You further expand the equation, okay, to consider the Q4. So you have your expand again, then you have your Z, okay. So you can try this at home, okay. You can try this at home to get the answer, okay. And there is already answer there. So for what if Q4, when we try to put Q4, so it's just same thing. What is experienced by Q4 is the charge, the potential from 1 to 4 plus what is the other combination is 4, 2 to 4, and then 3 to 4, right? Okay. And then it's also start expressing coming from Q3 and coming from Q2, okay. So what is Q3 just now? V31, okay, here, plus V32, okay. What is the Q2 just now? Q2 V1, okay. So you have this and you have this already, so don't waste your time, okay. You only need to solve this, okay. So this you get answer from here, okay, here and here, then you just need to solve this, okay. This one is you will solve using like the Q1 over then the distance between this 0.1 to 0.4. So but of course you have 4 pi epsilon naught, then in bracket, then you have the position, okay, of the fourth position is 0, 0, 1 minus 0, 0, 0, okay, here, okay. This is for this one, and for this one you need to calculate separately, okay. So with that, we finish also the almost finished this chapter, okay. You guys need to read the study cookbooks also, okay, on page 156, okay? Page 156. Need to read further details on the derivations, okay? I don't derive this in class, okay? And you also can see that actually there are various ways to get the energy stored. Here, you see, it's also WE equals to half D vector E equals to half epsilon naught E square and equals to D square over 2 epsilon naught. Okay, don't memorize. Okay, if possible, don't memorize. Try to understand, because you see this one is just interrelated with here. Okay, you just put D epsilon naught. Okay, equation. And this half D is you get it from here. Okay. So okay, with that we finish our week 4. Okay. Try to do the answer in the tutorial. Okay. If you guys in the tutorial, if you guys post the forum. Okay. At the forum, you can create new announcement. Okay, new announcement. And you can put like maybe tutorial 1 question 3. Okay, if I receive four replies from the group leader, means the group already done it, I will reply the 5th. Okay, or if I will always check, but if I didn't, please let me know. Why I'm doing this is that to ensure that all of you do the work. I mean, all of you actually try the tutorial question. Okay, and I put you in groups so that you guys learn and try to help one another. EMT is about exercise. I'm sure mathematical capability and knowledge, everyone is vary, okay, one from one to another. So some may solve the question faster, some may take times. But the why I'm putting you in group is that so that you guys may help each other. There is no mark to submit. Okay, that's why I'm changing from exercise to forum now. Exercise also didn't have marks. Okay, I want you guys to help one another. Okay, and tutorial should be solved individually. If you notice that you cannot solve this tutorial individually, first, then you need to work harder. Okay, because this tutorial should be solved individually. However, if you guys in the group, if you still struggle, then you really need to try a lot harder. Okay, EMT is about mathematics, and it will require much practice. You need to practice more in order. Sometimes you need to practice more in order to see in which situation that you will use Coulomb's law, in which situation you use Gauss law, and which coordinate is the suitable one, like Cartesian, cylindrical, or spherical. Okay, there are a lot of things that you need. You can do solve the question faster if you do a lot of exercise, because you will know which one is suitable to be used to solve that kind of situation. Okay, for example. Okay, so with that, I'm finished the week 4 what should be covered in the week 4. Okay, if any you guys have problem, feel free to contact me, or to post in forum. I will help accordingly. Okay, thank you.